Okay, so we are starting Unit 6, Level 2. Our learning targets are that you can identify and evaluate exponential functions, which is definitely a primary focus for today. You should also be able to write a rule to describe exponential functions displayed in a table of numbers. And you should also be able to graph exponential functions when we're done with this video. So you guys have seen these images a couple of times already this year. Linear functions we spent Unit 4 discussing, and that's when we have x to the first power. We will get to quadratics, but currently we are on exponential. And we're going to talk about what makes this family different from the others. And we can see a few different things happening here with how their graphs appear and how their equations appear. But this whole unit is about the exponential family. So why is the exponential family unique from the others? The first is that the x is an exponent. So I can see this is an example of the most basic version of the exponential family, y equals 2 to the x power, where x is an exponent. So this is how we identify that it belongs to the exponential family, is that the x is an exponent. The graph makes a curve, which we can see with this example that it's actually goes all the way here and then curves up, and there's not arrows printed on the graph, but it's implied that it goes forever up and out, and that this line gets really, really, really close to the x-axis, but it never actually touches the x-axis. And so it goes up the domain, or I'm sorry, up the range forever and ever. And so let's talk about that. The domain, which is where the graph exists along the x-axis, it will eventually go all the way to the right and all the way to the left, which means that the domain would be all real numbers, or negative infinity to positive infinity, however you want to say it. The range is where this exists along the y-axis. And along the y-axis, what happens is it actually never crosses or touches the x-axis. So along the range, it never drops below the x-axis, which is where y is equal to 0. So the range is always going to be where y is greater than 0. This yellow line that I just drew represents an asymptote, which is a line or a spot on the graph where the graph will get really, really, really close to, but never actually touch. And so this one is at y equals 0. So it just means that the graph that we drew will approach y equals 0. It'll get really, really, really close, but it's never actually going to be 0. And we can explain why that makes sense in a second. Here is the table for that. So if I were to plug in a 1 for this equation, it would be 2 to the first power. 2 to the first power is 2. And what I can see is that to go down this table, I would have to multiply by 2. The table grows through multiplication. However, sometimes it grows through division. So in this case, since we're multiplying by 2 to move down every time, if I wanted to move up the table, I would just divide by 2. And what happens when you divide by 2, just because my table stops at -2, it doesn't mean that that's where the graph ends. If I take 0.25 and I divide it by 2 again, I get 0.125. If I keep dividing this by 2, my number keeps getting really, really small, but it is never going to get to 0, ever. It gets infinitely close, but it never touches it and it never becomes negative, which is why there's an asymptote, because this is going to keep getting closer and closer and closer, but it's never going to be 0. It's never going to cross over into the negative. And so all of our exponential families will have an asymptote somewhere. Sometimes it shifts up or down, but this is where it is for this graph. So the x is the exponent, the graph makes a curve, and then the table grows through multiplication, or it can grow through division. The domain is almost always going to be all real numbers. The range usually is only going to exist on the top half, occasionally on the bottom half, and then the asymptote, there's always an asymptote. Okay, so we're going to just do a bunch of different situations here and show you how they relate, the table, the graph, the equation, the situation, they all relate to one another. So on Monday, Jackson left a half-eaten apple in his locker. Later that day, he noticed 2 ants. On Tuesday, each ant had attracted 3 more ants. On Wednesday, again, each ant attracted 3 more ants. If this trend continues, how many ants would be in his locker on Thursday? So, to draw a picture, hit pause and try to draw a picture. We have 2 ants to start. But on the next day, and actually on day 0, this is where we start, we have 2 ants. But after a day, this ant attracts 3 more, and this one attracts 3 more. So after the first day, I have a total now, I have 6. Or how many? Yeah. So now from here, this one is going to attract 3, 3, 3. So how many do I have now? 3, 6, 9, 12, 15, 18. And I can keep going, but you can see that this number is going to get really big really fast. So what I'm noticing is that I'm actually multiplying by 3 every time. So I can continue to fill in this chart by multiplying by 3 every time. Now that I've filled in the table, I can plot these points. The start, 0, 2, I'm going to approximate that it's right about there. This is where I'm going to start, but notice that this is also the y-intercept. Okay? And that's always going to be true. When x is at 0, we're always dealing with our y-intercept. Here we go. And so when I continue to graph those points, I've got 1, 6, 2, 18, and then the next one is off the charts. So I'm going to do my best to connect these in a curved fashion. And when I'm filling in the equation, the A value is always where we are starting, our starting amount, or our y-intercept. The B is always our growth, which we call our multiplier when we deal with exponential functions, because this table and graph grows through multiplication. So if I were to write the equation, hit pause and see if you can figure out what numbers you would plug in for A and B. Our starting amount was 2, and it grew by 3, a multiplier of 3. So that's our equation. So our y-intercept here, we said, is 2. Our asymptote, again, if I were to move up this table and keep dividing by 3, divide by 3, divide by 3, the same thing's true. The asymptote's going to be at y equals 0. This is going to get infinitely close to 0 if I were to continue in the opposite direction, but it's never actually going to get to 0. In the domain and range, this is kind of tricky. For the domain, I think we can talk about this in the form of the situation we have, which is the ants. We're never going to get negative ants, so I'm going to say that the domain starts along the x-axis at 0. It's always going to be greater than or equal to 0. And our range in this case is always going to be greater than 2, if we're thinking about it as a story problem and not what this graph and table and equation are capable of. Okay, so I'm going to read this to you. We have a zombie apocalypse has come to Anchor Bay High School. The first day, 5 zombies were discovered. Every day, each zombie infects 3 new people. If the population of Anchor Bay is 1,833, how many days until there are no people left to infect? Oh, I never went back and, hold up, I never answered this question. How many ants would it be in his locker on Thursday? So this was Monday, Tuesday, Wednesday, Thursday. The answer would be 54 ants. And we can see through this table that it grows very quickly. That's a sign of an exponential function. The numbers get very big very fast. Okay, back to this one. So go ahead and hit pause and see if you can fill out this page on your own. And draw a picture if you need to. So when we start, we have 5 zombies. And then every day, each zombie affects 3 new people. So if I have 5 to start, now this guy's going to get 3, 3, 3, 3, 3. So how many would that be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It grows by 3, but when we know that this table is going to be growing through multiplication, that means that when it grows by 3, then it's really going to be multiplying by 3. And so if I continue to multiply this by 3 every time to continue moving down the table, I end up with this. So take a second, hit pause, fill this in with your calculator, continue to multiply by 3 every time, and then plot your graph. Okay, if you haven't, hit pause and fill in your graph. Our y-intercept is at 0, 5. This is where our situation starts. And then 115, 245, and then we're off the charts because, again, it grows exponentially, which means it gets really big really fast. These numbers got huge. So this is what our graph is going to look like. Take a second. Remember, A represents your starting amount or your y-intercept. B represents your growth or your multiplier. So hit pause and see if you can write in this equation. Our starting amount is 5. It's growing by a multiplier of 3. And so here's our equation. And then finally it said how many days until there are no people left to infect. We know that we have 1,833. So how many days? 1,833 falls between day 5 and 6. So I would say after 5 days, because somewhere between day 5 and day 6, everybody's a zombie. Mrs. Bush's son put 2 stickers on her dining room table. The next day, she noticed the number doubled, and now there were 4 stickers. If this rate continues, how many stickers would be on her table on the 5th day? Hit pause and try to fill in all of these representations. To start, we had 2. Then it doubled, so we multiplied by 2 and it became 4. If it continues to double, we have 8, 16, 32, and 64. On the graph, that looks like this. And again, the number begins to grow very quickly. Our equation, the starting amount was 2, the multiplier was 2, and there we are. How many would be on the 5th day? 64 stickers is a lot of stickers. All right, the last thing here, evaluate the function. So this is kind of coming back up to identify and evaluate the exponential functions. Evaluate just means plug it in. So for each of these, we're being given a little bit of a scenario. The equation is already given to us, so we just need to figure out what number do we need to plug in to answer the question. If Ethan invests $1,000 and the equation is represented below, so here's our 1,000, he's starting off with $1,000, and we can see that this is where, in the form of A is our 1,000, our multiplier or growth is 1.06. How much money will he have after 10 years? 10 is what I need to plug in. So y is equal to 1,000 times 1.06 to the 10th power. So how much money would he have? You should practice putting this in your calculator. I'd say 1,000 and then 1.06. Then I'm going to use this little caret symbol here to raise it up to an exponent, and I'm going to plug in 10. Then I hit enter, and that means he would have, it doesn't tell us to round any particular way, so he'd have 1,790, and I'm going to round it to 85 cents. When we're talking about money, it makes sense to keep 2 decimal places. And there we are. That's it. All I had to do was plug in the number to figure this out. And you're going to have some homework problems like this. There were 500 packages of toilet paper at Meijer before COVID began. They disappeared quickly, and the equation is represented below. How many packages were available after the 5th day? Okay, so there's our starting amount of toilet paper, and they disappeared quickly. So it looks like we had half. Every day there was half the amount. So if I'm plugging this in, on the 5th day is what I'm plugging in for x. And there's a couple of ways. I can either put in a fraction, or I could put in it as 0.5. It doesn't matter. I'm going to do 1 divided by 2 because that's how I write my fractions. I put them in parentheses and use the division sign. And then the little caret symbol. And 5. So 15.625. So how many packages were available after the 5th day? We would round down because we don't have a total of 16. We would have a maximum of 15. So I'm going to make the little squiggly equal sign, which means approximately 15 packages. A sickness at daycare can be modeled with the equation below. How many kids are sick after the 4th day? So first, 2 kids are sick to start. Then every day it grows by a factor of 3. 2 times 3 to the 4th power. 2 times 3 to the 4th power. 162, that's a huge amount. That's exponential. They grow very quickly. The numbers get big fast. We started with 2 on the 1st day, and after the 4th day we have 162. Okay, so your homework is on the next 3 pages. They're all pretty easy and pretty fast. They just take up a lot of space on your paper. So make sure you finish the next 3 pages and ask questions if you have them.